Ever feel like you're drowning in information? You just want to understand the big picture, the important stuff,
Right.
without having to read like a 1,000-page textbook. You know what I mean? Well, that's what we're all about here. Today, we're taking a deep dive into probability.
Yeah, probability.
It might sound a little intimidating, a bit mathy, but honestly, it's everywhere. It's fundamental to like understanding how the world works.
Oh, absolutely.
And we're going to break it down. We're
Yeah.
going to make those core ideas crystal clear, nice and easy to understand, using examples that you can relate to that you see every day.
So you walk away and you're like, okay, I get it.
Right.
Yeah.
So you can actually use this stuff. So what do we have? What are we working with today?
Okay, so we've got this section from a learning resource. It's actually really well put together. It explains probability in a way that like anyone can grasp.
Awesome.
Yeah, it goes into both theoretical probability, which is like, the ideal scenarios, your dice rolls, flipping coins, all that good stuff. Right, exactly. And then it also covers empirical probability. That's where things get real.
Real world.
Real world, exactly. Looking at actual data, like, population trends,
Oh, interesting.
even genetics. So our mission here is to pull out those key insights, those golden nuggets,
Yeah, yeah.
and give you a practical understanding.
Huh.
No jargon, just the good stuff.
Okay, I'm ready.
All right, let's dive in.
Let's do it.
Okay.
First things first, define our terms, right?
Uh,
This section starts off talking about something called an experiment.
An experiment, yeah.
Now, hold on. Don't picture like a lab coat and beakers and all that.
Right.
We're not talking about that kind of experiment.
No. Oh,
In
yeah.
probability, an experiment is basically anything that happens, any action or event where you don't know for sure what the outcome's going to be.
What? It's uncertain.
Uncertain. So think about flipping a coin.
Yeah.
Heads or tails. You don't know until it lands. Or, drawing a card from a deck.
Right.
What are you going to get? Could be anything.
Or even the weather tomorrow.
Oh, yeah.
Will it rain? Will it be sunny? It's all an experiment in probability terms.
I like that. Okay, so we've got our experiment. Now, what about this thing called sample space?
Okay, sample space. It's a big word, but it's a simple idea.
Break it down for us.
It's basically just a list. It's every single possible outcome of our experiment.
Every single one.
Every single one, yeah. And it's often shown by the letter S. So let's take that dice roll.
The classic dice roll, yeah.
Yeah, our six-sided die.
Mhm.
Your sample space would be, get ready for this, 1, 2, 3, 4, 5, 6.
It's all the possibilities right there in curly brackets. Boom. I love it.
All laid out nice and neat. Now, within that sample space, we have something called an event,
Okay, what's an event?
usually shown by the letter E.
E for event makes sense.
Yeah, and it's basically any specific outcome
Yeah.
or group of outcomes that we're interested in. It's like a subset of our sample space.
Okay, so the sample space is the whole playing field, and the event is like the specific zone we're focusing on.
Exactly, you got it. Now, here comes the juicy part. Theoretical probability.
Ooh, theoretical probability sounds fancy.
A little bit, but it's really not that complicated.
Okay, good.
It's the probability of an event happening when we assume, and this is important, when we assume that every outcome in our sample space has the exact same chance of happening.
Like a level playing field.
Exactly, level playing field. It's all fair and square. And there's a formula for this.
There's always a formula.
Of course, it's probability, right? So it's P, open parenthesis, E, close parenthesis, equals, and I know this looks a little complicated, but stick with me.
I'm trying to keep up.
N, open parenthesis, E, close parenthesis, divided by N, open parenthesis, S, close parenthesis.
Okay, can we translate that? What does all that mean?
Okay, so P of G, that's the probability of our event E happening. N of E, that's the number of ways our event can happen.
Okay.
And N of S, that's the total number of possible outcomes, which is our sample space.
Oh, okay, I'm starting to see it now. So it's basically a fraction, right?
It is a fraction.
The top part is how many ways our specific thing can happen.
Yep.
And the bottom part is all the possible things that could happen.
Exactly. You're a natural.
Okay, let's put this into practice. Back to our trusty six-sided die. What's the theoretical probability of rolling a 3?
All right, let's break it down. Our sample space, remember S, is 1, 2, 3, 4, 5, 6. So the total number of possible outcomes, that's N of S, is 6.
6 sides, 6 possibilities.
Makes sense, right?
Right.
Now, our event, E, is rolling a 3. That's just one specific outcome. So N of E, the number of ways to get a 3, is just 1.
Just 1, yep.
So plugging those numbers into our fancy formula, the probability of rolling a 3, that's P of E, is 1 divided by 6, or 1/6.
1 out of 6 chances. Got it.
As easy as that.
Okay, I'm feeling good about this. Let's try another one. What about rolling an even number? What's the probability of that?
All right, same die, same sample space. 1, 2, 3, 4, 5, 6. So n of s is still 6.
Still 6.
But now our event E is rolling an even number. We've got 2, 4, and 6.
So 3 possibilities this time.
You got it. So n of E is 3. Therefore, the probability of rolling an even number, P of E, is 3 divided by 6, which we can simplify to 1/2.
50-50 chance.
Exactly, 50-50.
Okay, let's keep this train rolling.
I like it.
What's the probability of rolling a number less than 5?
Less than 5. Okay, same die, so n of s is still 6. Our event rolling less than 5, that includes 1, 2, 3, and 4.
4 numbers.
4 numbers. That means n of E is 4. So our probability, P of E, is 4 divided by 6, which simplifies to 2/3.
All right. I'm starting to see the pattern here.
Getting it.
The source also throws in a couple of curveballs, like, what's the probability of rolling a number less than 10 on this standard die?
Ooh, I like this one. It makes you think a little differently.
It does.
Because our sample space, 1 through 6, all of those numbers are less than 10, right?
That's true, yeah.
So our event E is actually the entire sample space.
Whoa, the whole thing.
The whole enchilada.
Yeah.
Which means n of E, the number of ways to get a number less than 10, is also 6.
It's like a guaranteed win.
It is guaranteed win. So our probability, P of E, is 6 divided by 6, which equals 1.
1. That means it's certain to happen.
Absolutely. And the source emphasizes that any event that is certain to occur has a probability of 1. It's a sure thing.
It's a lock.
Yeah.
Now, what about the opposite? What if we try to roll a number greater than 6 on this same die?
Now we're talking about the impossible.
Impossibly.
Because look at our sample space. 1, 2, 3, 4, 5, 6.
Yeah.
There's nothing greater than 6 there.
Nope, not a single one.
So our event, rolling a number greater than 6, it's an empty set. It can't happen.
So n of E is 0.
Exactly, 0.
Yep.
And 0 divided by anything is always 0. So the probability of rolling a number greater than 6 on this die is 0. It just can't happen.
It's a mathematical impossibility.
It is. And the source points out that any event that's impossible has a probability of 0. It's just not going to happen.
I love how these die roll examples make the concept so clear.
Yeah, they're really helpful for getting the basics down.
Now, the source also delves into another classic way to illustrate probability: playing cards.
Oh, playing cards, another good one.
So let's imagine we have a standard deck of 52 cards.
The good old 52.
We shuffle it up, draw one card at random. What's the probability of that card being a king?
All right, so now our sample space is every single card in that deck.
All 52 of them.
All 52. So n of s, our total number of possible outcomes, is 52. Now, the event E, drawing a king, there are 4 kings in a deck, 1 for each suit.
Hearts, diamonds, spades, clubs.
You got it. So n of E, the number of ways to get a king, is 4. So the probability of drawing a king, P of E, is 4 divided by 52. And that simplifies to 1/13.
1 in 13 chance. Okay, what about the probability of drawing a heart? Any heart.
All right, same deck, same sample space, 52 cards. So n of s is still 52. Now, our event, drawing a heart, there are 13 hearts in a deck.
Right, ace through king.
Exactly. So n of E, the number of ways to get a heart, is 13. So the probability of drawing a heart, P of E, is 13 divided by 52. And that simplifies to 1/4.
1 in 4. That makes sense. 4 suits, equal chance of getting any of them.
Makes sense, right?
Okay, last card question. What's the probability of drawing the king of hearts specifically?
Okay, getting specific now.
Very specific.
All right, so again, our sample space is still all 52 cards. N of s equals 52. But our event, drawing the king of hearts, there's only one of those in the whole deck.
That unique card.
That's right. So n of E, the number of ways to get the king of hearts, is just 1. So the probability, P of E, is 1 divided by 52.
1 in 52 chance. That's pretty slim.
Pretty slim, yeah. And to highlight something really important, the more specific your event becomes, the lower the probability is going to be.
Oh, that's interesting.
Yeah, as long as all the individual outcomes are still equally likely.
Right. Because we're still working with that theoretical probability.
Exactly.
Now, the source takes a really interesting turn. It applies these probability ideas to something completely different: genetics.
Oh, yeah.
Specifically, the example of cystic fibrosis.
That's fascinating. How does probability fit in with genetics?
Well, the source explains it like this. Every person has 2 genes that relate to cystic fibrosis.
2 genes.
We can represent them with letters: C for the normal gene and lowercase c for the defective gene. Now, if both parents are carriers, meaning they each have one normal gene and one defective gene, so they're both CC.
CC.
There are 4 different combinations their child could inherit.
4 combinations.
You could have CC, you could have CC, you could have CC, and you could have CC.
Oh,
So those 4 combinations are our sample space.
okay. That's our S.
Our S, and they're all equally likely.
They are.
So N of S, our total number of possible outcomes, is 4. Now, what's the event we're interested in?
Yeah. What are we looking for?
Well, we want to know the probability of the child actually having cystic fibrosis. And the source explains that this only happens when the child inherits 2 copies of the defective gene.
So that's the CC combination.
That's the CC combination. So our event E is just CC.
Just one outcome.
One outcome. So N of E, the number of ways to get CC, is just 1.
1.
Therefore, the theoretical probability of the child having cystic fibrosis is 1 divided by 4.
1/4.
1 in 4 chance.
Wow.
It's not just about games of chance. It's about understanding real-life situations,
Yeah, heavy stuff.
Yeah, and it highlights how, even a small probability, like 1 in 4, can have a huge impact.
It can. This is why genetic counseling is so important.
Right, exactly.
Because it helps potential parents understand these probabilities.
Understand the risks.
The risks, yeah. So we've talked a lot about theoretical probability.
We have.
Assuming those equally likely outcomes.
Right.
But the source also talks about this other kind of probability. Empirical probability.
Empirical, okay. So what's the difference? How is that different from theoretical probability?
Well, theoretical is all about what should happen in this perfect world, right?
Yeah, like ideal conditions.
Exactly. But empirical probability, that's where we get real. We look at what actually happens.
We look at the data.
The data.
Yeah.
We go out and collect it.
Observe.
Observe, exactly.
Mm-hmm.
And the formula for empirical probability is a little bit different.
Okay, how so?
So it's P of E, the probability of our event, equals the number of times E is observed divided by the total number of observations.
So instead of listing out the sample space and assuming things are equally likely, we just count up how many times something actually happens.
Yeah, got it.
We base it on real-world data.
Real-world data. And the source uses this cool example from the U.S. Census Bureau back in 2010.
The census, okay.
Yeah, they looked at the marital status and gender of people aged 15 and older.
That's a lot of people.
It is, a whopping 242 million people.
Wow. Okay, so what can we learn from that data?
Well, we can calculate some empirical probabilities.
Oh, okay.
For example, the data showed there were about 24 million divorced people in that group.
24 million?
Yeah, so if you randomly pick someone from that whole group, the probability of them being divorced would be 24 million divided by 242 million.
It's like a snapshot of divorce rates at that time.
Exactly. A snapshot based on real data. And that comes out to about 0.10 or 10%.
10%. Okay, what about gender? What can we learn about that from the census data?
Well, the data showed that out of those 242 million people, I got 124 million were female.
Okay.
So the probability of randomly picking a female from that group would be 124 million divided by 242 million.
Which is?
About 0.51 or 51%.
51%. So slightly more females in that age group.
Slightly more, yeah.
And that's based on actual observations, not just theoretical assumptions. I think these census examples really show the power of empirical probability. You couldn't just sit down with a piece of paper and figure out the probability of someone being divorced.
Yep.
You need that real world data. You need to see what's actually happening.
You do. It highlights how, real life is often messier than those perfect theoretical scenarios.
It is. It is. So we've covered a lot of ground today.
We have.
We started with the very basics. Experiments, sample spaces, events.
Right.
Then we dove into theoretical probability, calculating those chances in ideal situations, using dice rolls, playing cards. We even touched on genetics.
Yeah, we did.
And then we explored empirical probability, using real-world data from the census to understand likelihood in a different way.
Two sides of the same coin, really.
They are. And the takeaway here, the big takeaway, is that understanding these basic concepts of probability gives you a huge advantage. It helps you interpret information, make better decisions, understand the world around you.
Whether you're looking at statistics in the news or just trying to figure out the odds of something happening in your own life.
Exactly. So here's a final thought for you to chew on. Think about how these concepts, theoretical and empirical probability, might change how you view the chances of things happening in your own life.
Yeah, that's a good one.
Where do you see those differences between what could happen in theory versus what's more likely to happen based on what you've observed or the data you have. Think about that. And until our next deep dive, keep questioning, keep learning.
Keep exploring.
We'll see you next time.
See you then.